find was the challenging part about this problem? There is a challenging part to this. Yeah.
We are only finding above the x-axis, and actually on the domain, when it goes below 0, it shows the larger area, so I don't know why we...
Right, so really the domain from negative pi to 0 is just kind of weird, and we just throw that away, because there is no area above the x-axis as inscribed. Yeah. All right, so that's the first strange thing about this, is that this part here turns out to be irrelevant. So we just have to recognize that for that way. There's a second strange thing about this. What else did you find challenging?
I kind of found it hard to find the length of the rectangle.
Yes. Yeah. Figuring out what the horizontal distance for that rectangle is. The horizontal length is a challenge. What did you end up doing, Charlie?
Guessing.
All right. See if you can do a little better than that.
Well, it was educating.
Okay. What went into your educatedness?
Well, the 0 over there is in pi.
Yeah.
And then I drew a rectangle in the curve. And then marked the point farther out and on the x-axis. Well, that one's x sine x. And then that one's x sine x.
Okay. You're doing something really good here, and that is that you're marking up coordinates and not distances. If you marked this distance x right there, you were going to have a bad time. We want to mark coordinates and not distances. Okay. So let me undo it one stroke at a time. All right. That being said, now the tricky part. What is this coordinate right here? That's it. That coordinate is pi minus x. And the key here is to recognize that the sine has the property that whatever angle you have, pi minus that angle will give you the exact same y coordinate on the unit circle. It's the exact same way. You could also do it as a matter of symmetry, right? Okay? So that being said then, what is the length of the rectangle now? The length of that rectangle would clearly have to be pi minus 2x. Well, this is actually a little strange. It would be 2x minus pi. That's what this would be, because it's going to be final minus initial. Keep in mind that x is larger than pi over 2 in Charlie's diagram, so 2x is going to be larger than pi. Okay? What about this? Well, we already know sine x minus 0. And so this was the hard part, just getting this rectangle right here. And so we have area is equal to 2x minus pi sine x. And now we're ready to take a derivative. And that's going to give us 2x minus pi times cosine x plus 2 from sine x. And that now has to equal 0 to get our critical points. Okay, so here's how we're going to mark this. If they got an area function that looks like this, you could also have pi minus 2x if their x is over here. Then they get a point. But even if they did not, if their area function is in the form of some linear function of x times sine x, if their area function is in that form, then they are eligible for the other points that follow. You're going to get 1 point for taking a derivative and taking the derivative correctly of your particular area function. Yes.
Why coordinate in that 1 minus sine x?
Here?
No. Like for the area equation.
Think in terms of coordinates. So this is definitely sine x, right? It's on the curve, and the curve is y equals sine x. and this is definitely 0, so the distance here is sin x minus 0.
Why is it 2x on the square?
So it's always going to be right minus left. So we have x minus pi minus x. That's the beauty of marking up coordinates, is that you can find distance by subtraction every single time. Alright, so now we set this equal to 0, and now we have to go to the calculator to find the solution, because I can't solve this with elementary. Oh, and my calculator is still broken all bad. Watch this. It's going to tell me my license has expired. So let me get my real calculator. Oh, Philip, you have my real calculator. Yeah? Give it to me. I have my real calculator. Okay, what do I do with this? You put it in my hand?
Yep.
That's a new load. No, actually, I'm still missing one out of my 4. Hey, Philip, can you check somewhere? Because I don't actually have it. And I don't. Well, let me check. Oh, I put it in my jacket. Look at that. Look at that. See what's there? Technology, I'll tell you. If Microsoft built cars, they would randomly stop in the middle of the highway. That wasn't Microsoft's fault, but I still work for them. Window, negative 0 to pi, y negative 2, second count to 0. Found. Okay. And so the 0 is going to be 1.53 or 5438. Now here's how you're going to do a point. You're going to give them a correct point for solving this equation right here, for setting it equal to 0 and solving. So if they have a different equation, that began with this form right here, then they're eligible for a point there. And now we can make an f prime number line right here. Make sure I've got the right point, because my derivative is actually changing signs from minus to plus, which would give me minimum area. No degree. You win. That's right.
Extra credit?
There, that's much better. There we go. So actually, this makes much more sense. There we go. So now I get 2.4311 as one solution, and then I get pi minus that. So 0.7105 as the other solution right there. This is much better. And just looking, then I can can see that my derivative changes from minus to plus to minus over these intervals. So now what I can do is a critical point endpoint argument, but it's a very simple one, because if I check the area at 0, then my area at 0 is going to give me sine of 0, which is 0. And I get an area of pi, which is going to give me sine of pi 0 again. And then the area at 2.4311 is guaranteed to be bigger than 0, and therefore I have a max. So, you're going to get 1 point for solving the equation here. You're going to get 1 point for doing either a critical point endpoint analysis. If they had a single critical point, they could also do an argument from that prime analysis. And it would look like this, that the area is increasing up to a critical point with decreasing thereafter. And then finally, we just need to answer the question so that the dimensions of my rectangle are going to be 2x minus pi, which is going to give me 1.7206, excuse me, and the height is equal to sine of x, which is going to be 0.65 inch. So this was a somewhat more advanced question in that we had to set up our length carefully, and then once we had that, everything kind of fell into place, as long as we had our calculator and radian method. Questions? Thoughts? Okay, very good. Well, so let's see here. Total points should be, I think it's out of 5, right? Is that right? 1, 2, 3, 1 point for your analysis here, and 1 point for answering the question. Yep. So out of 5. Sure. Where'd you get all that? Okay. When that kind of thing happens, well, so using symmetry could be a thing.
Yeah.
So pi over 2 minus x theta pi. Twice that. The other thing you can do is collect and say, hey, you know what area is going to be x times sine x. You just go, that isn't right, but
Yeah.
I'll get you something. I'm fine.
Why did you say
It's a weird idea. It shows a negative there
What kind of idea?
because if your x had been 0.710,
Oh,
then
the length would be, yeah.
yeah, your area would actually go back from there, yeah. 2x minus 5. Sure. Another way of putting it is we didn't even need to check this critical point because we know that that's going to give you the minimum for the area. Yeah. Okay, good, 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 good. Well, our Our goal for today is really simple, which is the first D test. And so we're going to get there, we need a definition, and then after we get a definition, we're going to go straight to the first D test. So we need to define a term that we used a lot last year. We're going to define changing signs. We're going to say that f of x changes signs at x equals c if there is a neighborhood around c such that, and let's be specific, we're going to say that f of x changes signs, here we go, from plus to minus around c, if there's a neighborhood around c such that f of x is positive for x between c minus delta and c, but f of x is negative for x between c and c plus delta. So the picture here is that I've got a c, and I have a delta neighborhood somewhere around here so that on this side of c, f of x is positive for every single value, and on that side of c, then f of x is negative for every single value. Does this guarantee that f of c is equal to 0? No. What's missing? What assumption is missing that would be required for that guarantee? What assumption do I have to add to this in order to get that f of c would have to be equal to 0? That's not specified here. Yes, I would have to assume that f is continuous, and I haven't said here that f is continuous. It might very well not be. It means continuity. Okay. So changing signs then from plus to minus does not imply that f of c is equal to 0. It simply says that f is positive to the left and negative to the right. And that's it. It could be that f of c is some other value because the function is discontinuous, or maybe even f of c does not exist. That can happen as well. So this would be an example of a function that changes signs from plus to minus at c. This would be an example of a function that changes signs from plus to minus at c. And this would be an example of a function that changes signs from plus to minus at c. All of those could work. Now that we have this, we're going to have a very easy theorem called the first derivative test. If f prime of x, notice here I'm talking now about the derivative of some function. If f prime of x changes signs at x equals c, and f is continuous at x equals c, then f of c is a local max. Now, why is this? Well, we've already basically done the proof here. This is just an application of our argument from the sign of f prime. c minus delta to c plus delta. In other words, if I have some function f, like so, here's my graph of f of x, and here is my critical point x equals c, and I'm now going to take some neighborhood around c so that f prime is positive here and negative there. Then, my argument from the sign of f prime tells me that f of c is the absolute maximum on this interval. And because it is a max on an open interval, it is therefore a local max. So that actually is harder to say than it is to see. My function is going up, and then it's going down in the local neighborhood. Hence, the local max. So you remember this from last year. It was pretty easy. The corresponding statement is if f prime changes sign, the minus plus at x equals c, and f is continuous, then f of c is a local min. And the first t-test is actually pretty strong, because not only does it give us positive results, local max, local min, but it also gives us negative results. If f prime of x does not change sign, at x equals c, then f of c is neither. I should say, and f is continuous. Why do I have to keep on saying and f is continuous? Well, because you can imagine easily constructing a function that has a local max that that fools the first t-test. So continuity is an important assumption. Take a look at this function, for example. Here comes my function, right there. F prime changes sign, and right here, ta-da, we have a local max.
Yes. For the last statement, could you just say f of x, or f of c is not a critical point?
It might be a critical point, actually. So that was one of the main thing I want to do today with this is to show you the pitfalls that can happen with first t-test. Because you guys are pretty comfortable probably with the bread and butter uses of the first t-test, right? Did this all last year, you're good with that. But so this is pitfall number 1. You got to check for continuity. Pitfall number 2 is you actually have to do that first t-test, because if I take f of x equals x cubed, right there, then f prime of x is equal to 3x squared, so that x equals 0 is a critical point. And here it comes, Charlie. X equals 0 is a critical point, but f prime does not change signs at x equals 0. And you can easily see that from the derivative. It's going to be positive when x is negative, and it's going to be positive when x is positive. What does this indicate about the behavior at x equals 0? Well, here comes f of x equals x cubed, and you know what the graph looks like. It goes like this, we have a nice little horizontal tangent right there, and then you keep on going back up. So that if f prime of c is equal to 0 and f prime does not change signs, we have a different feature. It's called a shelf point in the graph of x.
What is
What's that?
what is pitfall?
Oh, pitfall. A place that you can mess up by accident. Okay.
I did.
I don't even know that one.
In that case, then we have what's called a shelf. Here's another place that you could, this is pitfall number 1 again. Take f of x equals 1 over x squared. A naive student might go through and say, hey look, f prime is equal to negative 2 over x cubed, therefore f prime of 0 does not exist. Aha, critical point. And look at that. F prime is positive on for x is less than 0. And negative for x is greater than 0, so f of 0 must be a local max. Looking at the graph of f of x equals 1 over x squared, what do you think the problem is with declaring local max right there? Right, there is no f of 0. It's not a local max, so you have to check continuity before you go rushing off to declare your local maxes. Let me make sure I alerted you to all the pitfalls that I was thinking about. If you could just take scissors to those 5 pages and cut them apart. You got 6. Great.
Yeah, I got 6.
Okay.
Is there a
I think